Log on, tune in, find out. Another good idea from Cambridge.
Okay, thanks. So today I decided I'll talk about cohomology. Cohomology. So I'll start out with some very general theories. So the setup is x to s as a stack over the site S. So that's our base category endowed with a Grothendieck topology. Well, you can always think of schemes over some base scheme with the Untitled topology, or think of C infinity manifolds with the usual topology. So that's S. This is a category finite groupoids which satisfies the stack axioms. And then X has an induced topology. So it's a category endowed with a Grothendieck topology. This just means I have to specify what covers are. That's what specifies a Grothendieck topology. And so X to X is a family of morphisms in X with the same target. Is a covering family. If all these things lie over parameter spaces, parameter schemes. And this is a covering family if this down here is a covering family in S. That defines the Grothendieck topology. So X is a topology with a Grothendieck topology, so that means that's the definition of a site. So X is a site. And once you have a site, then you have sheaves and you have cohomology. So that defines cohomology. So let me just quickly, so X is a site. So sheaves on X in the context of my lectures, you can define them like this. So first of all, I want to say these are called big sheaves. And what are they? These are CFGs F over X with unique pullbacks. And for a general CFG, pullbacks are only unique up to isomorphism. But if there's if there's exactly one pullback in all situations where it could pull back, then it's a CFG with unique pullbacks is that's a pre-sheaf. And for such CFGs, stack axioms are reduced to sheaf axioms. So sheaf. So no, the condition is there exists a unique pullback always. So whenever I have a morphism in S and a family over S, there exists only one object in this category lying over T and only one morphism making this diagram commute. No choices. It's a unique one. So there is no choices to be made. There's only one possible choice for pullbacks. So this is unique. So abelian sheaves that just means f of x, so the fiber of my sheaf f over an object here, f of x, is an abelian group for all x, and the pullback maps. So if I have y to x, and I have are additive, right? That defines abelian sheaves, and these form an abelian category. Which, by the way, if you care about it, has enough injectives. And if F is such an abelian sheaf, I define the cohomology groups. Well, one way to define them. It's like that. That's the constant sheaf. Okay, so that's the definition of cohomology, and I want to say a few things about well, how to compute maybe. But first, let me remark, such a big sheaf, what I've defined up here, a big sheaf F over X defines for all X over S, so X is an object of X lying over S, a small sheaf on S, right? So this a small sheaf. This is a usual sheaf in the small site. So those are all the schemes. This with étale structure maps to S, right? Not that's. So I just restrict this sheaf to just all the étale maps to S. And so a big sheaf over X defines all these small sheaves for all families, small sheaves on the base of any family. And so notation for this one here, let's call this F sub S, even though, of course, it depends on X. I don't know, it's just bad notation. Let me give a few examples of sheaves. If I have a representable étale morphism of stacks, this is by definition a small sheaf. That's what I call small sheaf. I mean, you can easily see that such a thing will define one of these things. Well, for example, the constant sheaf Z you can construct in this way, as just take infinitely many copies of X, indexed by the integers. Or the constant sheaf C, so where you should think of the discrete topology on C. So those are like constant coefficients are examples of these small sheaves. Another example of a sheaf is the structure sheaf OX. So the value of the structure sheaf at an object is just so if little x is a family parameterized by S, the structure sheaf of X at X is just S of S by definition. So this is the structure sheaf. Yep.
Explain what a big sheaf on a stack is and what's a small sheaf on a sort of scheme is clear, but what is a small sheaf on a stack?
Yeah, this is what I've defined here. So this is, I meant this by definition. So by definition, a small sheaf on X is such a thing. It's given globally by a representable morphism with étale structure map. This is a structure sheaf on X. So this is not small, but it is representable, in fact, by the affine line. Over X. So this is not an étale morphism, right? So if your base is the complex numbers, then don't confuse this sheaf with this one. Here, this is infinitely many copies of X lying étale over X indexed by the complex numbers. So as you see with discrete topology, this is the actual affine line. So one-dimensional fibers. Right, so this is not small. This is an example of a big sheaf. This is actually an example of a quasi-coherent sheaf. So what's a quasi-coherent sheaf? By definition, that means that all these small sheaves on all these schemes are quasi-coherent sheaves on schemes. Quasi-coherent sheaf. This is a big sheaf F, such that Fs is quasi-coherent for all families. So such that that's the first condition and the second condition. Let me write it over here. For all pullback diagrams. So X is a family over S, which is pulled back to a family Y over T. I actually, this map, let's say F. So I have a small sheaf Fs and a small sheaf over T. And the pullback of this one, well, there's a canonical map. That should be an isomorphism for all these situations. This is not true for general big sheaves. But if these two conditions are satisfied, those are quasi-coherent sheaves on stacks. So this was, and then there's a third example I want to give. This is just to fix ideas. Let's say. I want all the objects in S to be smooth, so let me just stick to C infinity manifolds. And then I define so the sheaf, so X over S stack, and then let's see, so omega Q is defined by so this is a big sheaf. This satisfies the first condition. I mean, okay, an analog of the first condition, or if you work with schemes, this satisfies the first condition because Kähler differentials form coherent sheaves, but it doesn't satisfy the second condition if T and S have different dimension. This isn't true. So these are genuinely big sheaves. I'll give an example of cohomology. I mean, this is just to show you that how there's not. I mean, okay. Let's say F is O star. So. Yeah.
So a big sheaf is just a representable one.
No, no. These are, for example, not representable. This is of all these omega Q, the only one which is representable is omega 0, the structure sheaf. I mean, you wouldn't know. It's not a vector bundle because the rank isn't well defined. The rank of this coherent sheaf depends on the dimension of the base family. So just like, and this is very, okay, I don't know. First cohomology with values in O star. I mean, from general principles, these are isomorphism classes of extensions. Well, right. So here's the constant sheaf Z. Here, this is a sheaf represented by actually. So this is, if you want, by the multiplicative group. So this is the same as isomorphism classes of GM torsors, which is a property of representable morphisms of stacks to be a GM torsor. It's one. I mean, it's like one of those properties I defined yesterday. How to get from the extension to the torsor? Well, you can construct this fiber product. So from the extension to the torsor. This is also the isomorphism classes. Of line bundles on X, and so this is also pick X. If you have so if X, say, is a quotient stack, then this is the same as the G equivariant line bundles on X, or in general, if well, then this is well. Let me not. Okay. So a line bundle over U, and I have the two pullbacks to R, and I have an isomorphism between those two pullbacks such that a certain co-cycle condition is satisfied on the fiber product. Those are descent data. And so these things, make explicit, well, make it possible to calculate the Picard group in examples by doing this kind of thing. Oh, yeah, thanks. And just, I don't have time to do any calculations here, but just, you can do this as exercise. So the stack of elliptic curves has Picard group Z modulo 12Z. The weighted projective line with weights 4, 6, well, actually, doesn't depend on the weights. It's always just, okay. So one good way to calculate is check cohomology. So suppose R to U is a groupoid presentation for the algebraic stack X. So that means that R to U is the symmetry group of a complete inversal family. That's the terminology I've emphasized in the lectures. Often people call these groupoid presentations for stacks. Then construct a simplicial scheme. So x0 is U, x1 is R. In general, xp is the fiber product of p plus 1 factors of U over x. So this is a simplicial scheme. Right, so often, so U is now called x0, R is called x1, but now I've extended it. So x2 is the fiber product of R with itself over U, actually, and it keeps on going. And there's this simplicial scheme is augmented with this map to stack X. So then if F, this is a very general fact, if F is a big abelian sheaf on X, there exists an E1 spectral sequence So as I had explained, the big sheaf induces small sheaves on all of these schemes here. Right? Because every time I have a map from a scheme to X, that corresponds to a family parameterized by X1, for example. Right, so this is, and that goes to the cohomology of the stack. So this is the cohomology of the stack with values in the big sheaf, but these are all usual. So this is usual cohomology of small sheaf on étal site of the scheme. So that gives one approach to computing lots of cohomology groups. For example, suppose our stack has affine diagonal. So separated schemes, for example, or if the group scheme is affine. I mean, this is quite a general. Lots of stacks have this property. Then, without loss of generality, U can be chosen to be affine. I mean, say you have some groupoid presentation of your stack X. Well, you can take an affine open cover of U and construct a new, so then you get a new groupoid, which also presents X. And so you can always replace U by an affine open cover, and that makes U affine. So without loss of generality, U is affine. But then if U is affine, remember that, well, we can write this Cartesian square also as this Cartesian square. And then if the diagonal is affine, then this map is affine. So if U prime is affine, R prime is affine. So if U is affine and the diagonal is affine, that implies that all the xp are affine. And then if I have a coherent sheaf, all these things are coherent or quasi-coherent even, so all higher cohomology vanishes. And so for example, this tells us that if F is quasi-coherent, then the cohomology of the quasi-coherent sheaf on the stack X is just the check cohomology. So well, so the complex is this is an E1 spectral sequence. Okay, maybe that's all I want to say about the quasi-coherent sheaves. Let me talk about constant coefficients. To compute cohomology with constant coefficients, the easiest thing is maybe to pass from an algebraic stack. Let's assume the algebraic stack is smooth. Pass to the associated analytic stack, which is then a C infinity stack. And so let's just go over to the C infinity world, and then cohomology with constant coefficients can be computed using de Rham cohomology. So let's talk about de Rham cohomology. That seems a very concrete cohomology theory. So that means, so now my base category will be C infinity manifolds. And then the stack X will be associated to groupoids. These kind of groupoids, this is going to be a Lie groupoid, as it's called, meaning that R and U are C infinity manifolds, right? And S and T are, well, C infinity maps. That's a Lie groupoid. Oh, sorry, C infinity submersions. Instead of smooth. I mean, that's the correct analog of smooth. So then X is a simplicial manifold. Because these are C infinity submersions, all the fiber products I have to do to construct this simplicial scheme are fiber products with smooth maps with submersion, so all the fiber products exist. And I get a simplicial manifold. And then I write down the check de Rham double complex. And so this is inspired by, you can read a lot about this check de Rham complex in the classical case in the this book by Bott and Tu. And I mean, this is all modeled on their description of the, so let me just write down the very beginning of it. So there's a pullback map from x0 to x1 to x2 and so on. These are so alternating sums of pullback maps. So this is just the usual check differential. In the other direction, we have the de Rham differential. So this is this double complex. Let me remark that if I take the kernel of the check differential, I get so these are the kernel of this first map. I get the global sections of these various big sheaves I talked about before. I mean, for manifolds, you would only look at global sections of these sheaves and the de Rham differential, and that would compute cohomology. For stacks, that doesn't work. You have to look at the double complex.
What does it compute if you just did that?
Well, I don't know if it's anything sensible in general. So, the P de Rham cohomology of this differentiable stack X, this is the cohomology of the total complex of that double complex. And this is not hard to see using a little bit of homological algebra, that this is actually equal to the cohomology of the constant, of the cohomology of the stack X with constant coefficients in R. So in particular, it doesn't depend on the choice of the groupoid presentation. Just to give.
The fact that the Rham complex lies in the kernel is given by the theorem, right? Or is it like obvious?
The fact that these, I mean, this is basically just the fact that these are sheaves, and for sheaves, global sections are always the kernel of the first, of this first check boundary. Or you could take it as definition of the global sections, but it is the global sections anyway. These are global sections. E.g., if X were a quotient stack Lie group acting on a manifold, then, by the way, this simplicial scheme is just given by that. Then the de Rham cohomology of the stack turns out to be equivariant cohomology of X with values in the Lie group. So I won't be able to prove that here. For a proof, I should have mentioned, well, everything I'm going to say today you can read in these notes. So there's Trieste lecture notes. There's some lecture notes of mine on lectures in Trieste, and you can easily find them on the internet. Just to give you a very more concrete example, if X is just the quotient, I'm actually the classifying stack of a Lie group, of, let's say, of a compact Lie group G, then the de Rham cohomology of BG, so that's, I take the Lie algebra, the dual of the Lie algebra, the symmetric powers of that, and then the invariance under the Lie group. So for example, if we want to be the simplest non-trivial Lie group, the cohomology ring is polynomial ring in one variable in degree 2. So there's contributions in arbitrary high degrees. So let me just remark that there exists a product structure. So a cup product. So from now on, I'm going to talk about only de Rham cohomology, so I'm going to drop the de Rham and just write it like this. So there's a cup product, right, just combining the wedge product on forms and the usual cup product in check cohomology. Define something on the double complex, and you can define this cup product there. Okay, next, cohomology with compact supports. Now you need X to be oriented, which means that R to U is oriented, which means that R and U are oriented, and the source and target maps are also oriented. Compatibly, everything is oriented. And let me call the dimension of the stack N, and R the relative dimension of x0 over x, so that's the relative dimension of the source and target maps. So the compactly supported cohomology of X, this is the total cohomology of another double complex, which is just a slight variation. Okay. So here's a de Rham differential, raising degree by 1. Here is this is n plus 2r. Here is delta lower shriek. That's the alternating sum of integration along fibers. Which is well defined because I'm looking at compactly supported forms. So I hope from this you can see how this complex, you can extend it. So it's a third quadrant thing. And the degrees are that this thing here, that's in degree n. This is degree n minus 1. So the nth cohomology with compact support is really the compactly supported forms on this cover x0 divided by the images of these two things here. And then it goes down. And here I also, for future reference, the co-kernels of these delta shriek maps here. This is what I define to be the compactly supported forms on the stack. So these are the co-kernels. And if you really think about things, you see that that's the only natural way to define cohomology with compact supports. I mean, it's really just about simplicial manifolds, all this theory. Okay, we've got that. Okay, let me mention a few properties. So compactly supported cohomology is a module over the cohomology ring. So let's say, note that by a cap. So that you have that structure, and then you have the integral. I mean, the nth cohomology with compact supports, as I said, right, is these compactly supported forms divided by these images, and I can just take the integral of this form on x0, and notice that it vanishes on those two. So it's well-defined, induce a well-defined integral. And this induces a pairing. Okay, so that's the Poincaré duality pairing. And so we just need a small technical assumption. So assume X is a finite type, and I mean, since I'm working with bot and 2, this means that R, U admit finite good covers which are compatible, then you get Poincaré duality. So HP of X tensor Hn minus P C of X. This is a perfect pairing of finite dimensional vector spaces. So, for example, from this you can see that the compactly supported cohomology of the classifying stack of S1 has to be R if P is odd and negative and 0 else. Right, so cohomology goes off to positive infinite degrees. Cohomology with compact supports is in negative degrees. Okay. That kind of thing happens only for Artin stacks, so let's talk about Deligne-Mumford stacks. Now we assume that our groupoid is always étal, so source and target maps are local covering spaces. So in particular, all these xp in the simplicial scheme have the same dimension. And it's always the dimension of the stack. So, and another assumption that the diagonal is proper with finite fibers. So this is some kind of separation property of the stack, and automorphism groups are all finite. That's Deligne-Mumford stacks in the differential world. Okay. One can prove that the Ram cohomology of X is the case cohomology of the global sections. So what I have in yellow over there. Then for Deligne-Mumford stacks, it's just like for schemes, you only need this thing. You don't need the double complex. And also, the same thing is true for cohomology with compact supports. So in particular, all of these cohomologies vanish except for 0, except if k is in the interval from 0 to n. Right, so none of this going off to infinity, none of these things are in negative degrees. So this is one of the respects in which Deligne-Mumford stacks behave a lot like spaces. So now let me pass the proper, so that I now want to take integral, so I need proper stack. So this is in addition to what I already have over there in terms of assumptions. In addition, this means that assume the coarse moduli space which is just the topological, I'll just think of this as a topological space. This is a topological space given as U mod the equivalence relation R bar, which is the image. Right, the image of the groupoid in U times U is an equivalence relation in U times U. It's a closed equivalence relation, so this quotient will be a Hausdorff topological space. And so I assume that this coarse moduli space is compact. That means that that's the definition of proper stack. Then we have, in fact, that cohomology coincides with cohomology with compact supports. And the isomorphism is induced by, let's see, so, I mean, so cohomology classes of the stack X in degree K, they're represented by forms of degree K, global forms on X. Right? So these guys are represented by these, and these guys are represented by well, compactly supported forms. There's things in the co-kernel over there, and so right, these guys here, I pull them back to the cover X naught. These guys admit a map from the cover by construction. And here, R is 0, right? So the degrees in the horizontal lines don't change. So this is omega c k X naught. And so this map here is given as this composition where this is omega. So I have to go from a k form on X naught to one with compact supports, and I multiply by rho, where rho is a partition of unity for the groupoid with compact support. And so a partition of unity, so rho is a partition of unity with compact support, and rho being a partition of unity means that this condition. So So rho is a C infinity function u to r. This is x naught, right? Sorry, I've got double notation. So it's a function from x naught to r, C infinity. I pull it back to x1, and then I push it forward by integrating along the fibers. I should get 1. That is what the correct notion of partition of unity. Remark, not all groupoids admit partitions of unity, not all Étale groupoids. So you remark, you might have to pass to a different groupoid to pass to an open cover of U. Sorry, remark, may. Anyway, so. So in particular, if we have this isomorphism here, we had the integral. Now we have the integral on form. So there exists this integral x on top degree forms to r. And so given by the formula, if omega is an n form on x, then the integral of omega, I can compute it on x naught by, well, pulling back the form to x naught and then multiplying by the partition of unity and then integrating over x naught. And this induces then Poincaré duality on the cohomology of x. I don't need to put any c's anymore. So this is a perfect pairing. Okay, let me give the simplest of all possible examples of an integral where the dimension of the stack is 0, so a differentiable stack of the dimension 0. So x is really equivalent to just the disjoint union of BGI for finite groups. GI. So let me first just consider the case that x is BG for a finite group G. So then a groupoid, a Lie groupoid presenting this stack is, well, this zero-dimensional Lie group. So what is the partition of unity? It's a function on the one-point space, so just a number, such that when I pull it back and then push forward again, I get 1. So pushing forward means I have to integrate over the fibers of which there are, well, as many as there are elements in G. So pushing forward means multiplication by the cardinality of G. So if this process of pull back, push forward is going to give 1, the only choice for rho is that number, that real number. So this is the partition of unity. And then we have 1. There is a canonical element 1, the unit in the de Rham cohomology, the 0th one. So that, since x has dimension 0, I can integrate that over x. So by my formula, that is just 1 over the number of elements in G. So for a general x, which is this joint union of such things, I get the the stacky number of points of X, so which is the sum over the isomorphism classes in this finite groupoid over, well, in each isomorphism class, the number of automorphisms. Okay, now let me talk about intersection theory. So I'm going to do that via the cohomology class of a substack. So in general, let's just look at a proper map, a proper representable morphism of differentiable stacks. Well, that induces a wrong-way map on cohomology with compact supports. So because it's a proper map, if I pull back forms with compact support, they have compact supports. So dually, via Poincaré duality, I get a map which I denote F lower shriek. So that goes from, sorry, this was X to Y. So the dimension of Y minus I dimension of X minus I. So if I take this index up there to be 0, then I have the unit in there, so then F lower shriek of 1 is an H dimension X. Well, let me write this as the codimension. And that I'll write CL of Y as class of Y. Okay. That's how you can define in general. So in particular, for closed subschemes or anything mapping properly to X, you get a class. For example, if you have a vector bundle over your stack, let's say the rank is R with the 0 section, then you can define the Euler class of the vector bundle as, the 0 section defines the class of X in E. So this is class of X in E, and then you pull that back to X. That's just, for example, you can get the top Chern class, so that's the Euler class. Well, actually, this is not necessarily Euler class of E. So definition, if X is proper, Deligne-Mumford, then the Euler number of X is the integral of the Euler class of the tangent bundle. So if you have an étale groupoid presentation for your stack, then you have the tangent bundle of U and the tangent bundle of R define gluing data for a bundle on the stack. That's the tangent bundle of the stack. For arcing stacks, you can't do this because when you pull back the tangent bundle of U to R, it's not even the same rank as the tangent bundle of R. But for Étale groupoids, this works. Okay. That's the Euler number of a proper Deligne-Mumford stack. Here. There's a type of Gauss-Bonnet theorem for, proper smooth Deligne-Mumford stacks. Which says that this other number that I've defined over there as the integral over the top Chern class of the tangent bundle, or I should say the Euler class, this is equal to the orbifold Euler characteristic of X. And so what's the orbifold Euler characteristic of a Deligne-Mumford stack? So let's say this is chi orb of X. So if X is a variety, the orbifold characteristic is the usual topological Euler characteristic. And the other property is that if X to Y is a finite, so representable finite Étale cover of degree D, then the orbifold Euler characteristic of X is D times the orbifold Euler characteristic of Y. So these two properties, it's not hard to see that if you require these two properties, you get a unique definition of the orbifold Euler characteristic for Deligne-Mumford stacks, which don't have to be proper. But if your Deligne-Mumford stack is proper, then this orbifold Euler characteristic turns out to be equal to this integral. Okay. So those things are actually okay. So just to give you some examples, well, let's give you one example. This is a proper Deligne-Mumford stack. And so I'm going to compute this as the orbifold Euler characteristic. Well, what does this M bar 1, 1 look like? Well, there's a special point where the automorphism group of elliptic curve has 4 elements, and then there's where the automorphism group has 6 elements. Otherwise, there's always be Z2. But the rest, this is actually, the rest here is topologically C star. So it has no Euler characteristic. So this is just 1 over 4 plus 1 over 6 plus 0. So these are the 3 strata, this one, that one, and the rest, which has Euler characteristic 0 because it's just, the coarse moduli space is C star. It's a degree 1/2 cover of C star. Anyway, so that is. Just for the fun of it. If you just take the elliptic curves, so you get the previous result, 5/12, and you take out one copy of BZ2, so minus 1/2. Oh dear. Well, I wanted to talk about intersection numbers, so well, I'll just need a few minutes here. So let's say this is a pullback diagram. Assume that this fiber product is actually smooth. And all maps are representable, proper, and injective on tangent spaces, so submersions. Then, let's call this map here F. Call this map here U. So the cup product of the classes of Y and Z in X is the Euler class of the excess bundle of the intersection. So this is so U upper star of this normal bundle Y over X divided by the normal bundle of W over Z. So that's the excess bundle. This is not hard to reduce to the case of manifolds. I mean, none of these results I'm talking about are hard. They all reduce to the case of manifolds by taking covers. And I mean, you know, I've written down a statement that doesn't require any of these stacks to be globally proper. And that's why it's easy to. That's why it's a local, essentially local statement, which is easy to prove. And then, but then, now if X is proper, then we can define the intersection number and from this proposition, I just want to mention two special cases. So if one case is if Y and Z intersect transversally, which has the usual meaning, and if the dimension of Y plus the dimension of Z is equal to the dimension of X, then this intersection number is equal to the number of points of W in this stacky sense that I talked about over there. So these are typical rational numbers, not integers. So intersection numbers. Right. So transverse intersections you can compute by computing fiber products. And the other extreme case is the self-intersection case. If Y is equal to Z, then the self-intersection I can compute on W as the Euler number of the normal bundle. And I wanted to finish with one example of this last formula of a self-intersection. So if you allow me another 5 minutes maybe. Let's say X is M bar 1, 2, curves of genus 1 with 2 mark points. This is also the universal elliptic curve over M bar 1, 1. So a picture, there's M bar 1, 2, here's M bar 1, 1. So somewhere there's a rational fiber, well, over infinity, and the other fibers are elliptic curves. But there's, of course, all elliptic curves have a distinguished point, right? So this is the, and if I connect them all, then this is a section. So it maps M bar 1, 1 into M bar 1, 2. So this is a section, universal section. And so y will be M bar 1, 1. And so I want to compute this self. Sorry?
What does it mean that two stocks intersect transversely?
Well, you just, well, what does it mean usually? That the tangent space, every point from y and z, the tangent space generates the tangent space of x. I mean, just the usual definition for schemes just applies verbatim to the stacks, because I mean, the tangent spaces, I mean, all the tangent spaces of points of y are isomorphic to tangent spaces of points in the, étale cover. Right? So, I've got this map is étale, and so tangent spaces here, I can check anything. So I can cover all this by étale covers, and then I have a property of scheme. So this kind of thing, like intersecting transversely, is something you can check étale locally, therefore on the groupoid covers. So this self-intersection of the class of y and x, so by my self-intersection formula, this is, what did I write here? That should have been y. So this is, and if this is actually contained in x, I mean, of course, if no, you're right, and actually, I should W's, sorry, W's correct. Because I didn't assume in general that this y into x is actually an embedding. So this fiber products, even if this is y and that's y, that's not necessarily equal to y. But in my case here, this is a section, so this is actually an embedding in this fiber product. I have y here, y there, and y there. So in my case, this is actually the integral over M bar 1, 1 of this normal bundle to this section, which let's just call that n. So n. So that's what I wanted to compute. And so let me just try to do that. So I assume to do this, I'm going to choose a morphism from P1 to M bar 1, 1. Damn it. Here's M bar 1, 2. And the pullback I'll call E. This is some kind of elliptic fibration over P1. And I'm going to use such an elliptic fibration to do this computation. So let's call this thing F here, because then I have the formula that the normal bundle to the section here, if I compute its Euler number on P1, well, that's the pullback of this Euler number of the universal n. And the integral over P1 I can first push forward to here and then do the integral. So that's the integral over m bar 1, 1. So pulling back and pushing forward, that is just multiplication by the degree of that map. So this is the number I want to compute, and so I can solve for this number if I can compute this something on P1, and I can compute the degree of f. So the degree of f is twice the number of rational fibers. Why is that? Well, here I have a copy of BZ2 sitting inside m bar 1, 1. This is, this is the classifying segment. This is B of the automorphism of the singular fiber here. So if I pull this back, I get the support of all the rational fibers here. So this D is just the sum of all the points that have rational fibers. And so the degree of f is the degree of this map, but the degree of this map times 1/2 is the number of points in D. Right, so that proves this formula there. And well, this number is of course just the degree of this line bundle on P1. So let me call that the degree of this elliptic surface. So from these things, it follows that this number I want to compute is equal to the degree of my elliptic fibration over twice the number of rational fibers. And so again, there's this universal number computed on this moduli space. I can compute that using any such fibration. I mean, for any fibration, this quotient is going to be the same number. So this is for all such. And by the way, this is also equal to the number of rational fibers is actually the Euler characteristic of total space. So all the elliptic fibers have Euler characteristic 0, and the special fibers have Euler characteristic 1. Yeah? Yeah, I'm finished. I'm finished. Because now that this use as E over P1, the pencil of cubics through 8 generic points in P2, then E is the blow-up of P2 at 9 points. And so then the Euler characteristic of E is 12. You can compute that. And the degree is -1 because any one of the blown-up exceptional lines can serve as sections, and those have self-intersection -1. And so you can see that this number is -1 over 24. Thanks. Yeah, that's it.